Okay, let's move on to the second part of this lecture. We're going to talk about what is called the wave equation, where we can prove that the telegrapher's equation that we came up with in the last module define a moving wave. So this is just to remind you what the telegrapher's equations are, that the time derivative of either voltage or current is proportional to the spatial derivative of the other. There are additional terms here from the resistance and the admittance. But we are in most cases going to ignore that, and we're going to set R equals G equals 0. So let's take a look at the what we're going to call the wave equation. And so just to remind you, we've got dV dz equals minus L times di dt, and we've got that di dz equals minus C times dV dt. Okay, so let's prove that this makes a wave. To do that, I'm going to take the spatial derivative of this equation right here, of both sides. And so we're going to get a d squared v dz squared equals minus L times d squared I dt dz. All right, to this equation, I'm going to take the time derivative of both sides. So this will be di dt dz equals d squared v dt squared. All right, all kosher so far. Now you should notice that I've got this same term right here, d squared I. Let me do that in color. All right, I've got the same term in both of these two equations, d squared I with respect to, sorry, it's squared right there, with respect to dt dz. All right, so we can set these equal to each other, solve for them, and thereby removing them. And if we do that, we get the following. We get that d squared, go back to black, d squared v dz squared times minus 1 over L equals minus C times d squared v dt squared. Right? We can make a little tweak to that. Let's just bring the L over to the other side, right, and go like this. And let me just do this on a separate line. So the second derivative of voltage with respect to distance is equal to L times C times the second derivative of voltage with respect to time, right? The minus signs here canceled out on the two ends, right? So this is what we are left with. All right, so here we go. This is called the wave equation. I should say it's a simpler form of the wave equation, but it's the one that we are going to use right now to prove that a transmission line is in fact a conductor of moving waves. Now, we can do a whole class on differential equations in order for you to figure out what the answer to this is and what is the solution to this. But in this case, it might be easier to just write it down and prove to you that by inspection that we know what the solution to this is. And so the solution to this is going to look like the following. It's going to be V as a function of time and space equals, I'm going to write V positive times F of T minus Z square root of LC plus V negative times, so that's not an F, G of T plus Z times the square root of LC. All right. The solution, any solution that solves the wave equation is going to fit into this form right here. Right. Now let's take a look at this and examine and describe what this is. Let's break it down. Okay. V positive and V negative are constants, right? 5, 12, 36. Okay, they're just constants. So don't pay too much attention to that. Okay, F and G are going to be functions, right? They are the shape of something. It can be a sine wave. It can be a triangle. It can be a single impulse. It can be a little square or a square pulse. It's sort of any shape that evolves with time, or any shape or function. One-dimensional, right? This is a one-dimensional function because the argument t minus z square root of LC, even though it has both variables t and z in it, in the end, this argument here is just one number, right? So f is a one-dimensional function, and same for g. This is just another one-dimensional function. Again, it could be anything you want it to be. It can be a sine wave, it can be a square wave, it can be an impulse, but it's sort of any one-dimensional function that you can come up with. All right. So this is the wave equation, but let's actually visualize why this makes things move. And to simplify, let's say that, go back to black, channel your inner AC/DC. Let's just set V negative equal to 0 and V positive equal to 1. And we're going to set f of t to be something like this, right? It's it'll be 0, 0, 0, and then t equals 0 to jump up. It'll jump up, and then it'll ramp back down, and then flatline again. So this will be at t equals 2. Right, this is f of t. All right, so let's take a look at this equation and show why this is going to be a moving wave. So in that case, the voltage as a function of time and space will be equal to f of t minus z square root of LC. Okay, so let's actually plot what this means at different values of t. All right, so at t equals 0, right, the voltage at any location z at t equals 0 is going to be equal to f of minus c square root of LC. All right, so that function is going to look like this. The negative sign right here, this negative across the z, is going to take this function and it's going to flip it. It's going to mirror image it. Right, and the square root of LC is just going to squash it or stretch it. Right, so that function is going to look like this. It's going to be 0. Right when it crosses 0, it's going to jump up, and it's going to fall back down, and then flatline. And let's start with that. All right, so now next question is what happens a little bit of time later, right? At v of z and t equals 1, this will be f of 1 minus z times square root of LC. All right, so this function is going to be the same, except it's translated by 1 point, by 1 unit, in this case to the left. All right, so this represents t equals 0. This will be t equals 1. And going back to the blue, this function, if you plot it, will look like this. Right, it'll be the same thing, except it'll be translated at z equals 1. Right, this is a z right here. Right, so you can start to see that the wave is moving. It's moving in the positive direction. Right? So this element right here, this f of t minus z delta, z square root of L square root of c that comes from this is going to be a positive going wave. All right, you can repeat the same exercise and you're welcome to refer to the notes, but this second term right here is going to be a negative going wave. All right, so we can have the solution to the wave equation is a wave that's going in the positive direction and a wave that's going in the negative direction. Those two waves are completely independent of each other. You can have a sine wave going this way and a square wave going the other way. You can have an impulse going one way. That's what F and G are. It's the shape of the wave that's moving in the positive and negative directions, and they are independent of each other. They also can be different sizes. That's why V positive and V negative are separate from each other. But you can have either or both. One of them could be zero. You could have only a positive going wave if you like. But any solution to the wave equation is going to be structured in a form that can map to this. All right. So a positive and negative going wave. So that's the wave equation for voltage, right? But there's two more things that I want to talk about. The first is how does this work for current? And the second is what's the speed of the wave? So the speed of the wave we can get from this relationship right here, 1 minus z square root of LC, or if you prefer, t minus c square root of LC. All right, so the question we'd ask is, how long does it take for the wave to travel by exactly 1 meter or 1 unit in z? And if you take a look at this and sort of solve for it, it turns out to be 1 over the square root of LC is the time to travel by 1 meter. All right, so obviously the time it takes to travel 1 meter is the same as the speed. So we're going to call this propagation velocity equals 1 over the square root of LC. All right, this just fell out of the math of the wave equation, but fundamentally it's connected to the impedance and capacitance that are within our transmission line circuit. So this one's very important, definitely something worth memorizing. Vp equals 1 over square root of LC. But we've solved this for voltage. Okay, so this is the voltage wave equation, and it seems to work out very well. But the other half of this is current. What's going on with the current? So once you've got the voltage, you can figure out what the current is by going back to either one of our original telegrapher's equation. Pick your favorite, plug the current in, and let's say you plug the current in over here. First, take the derivative with respect to z, and then integrate with respect to time, and you can go from voltage to current and current to voltage and go backwards. If you apply that process, here's what you're going to get. You're going to get the following. You're going to get I of z at time t equals v positive divided by a quantity called z0 that I'm about to define times f of t minus z square root of LC plus the negative over z0 times g of t plus z square root of LC. All right, so you'll notice that this equation is almost identical to the voltage equation. Let me see if I can put them together. I believe I can. Oh, not easily. Hold on. Oh, it's possible. Nope. Okay. So I'll forget that. Take a look at this voltage equation right here. Right, you've got V positive times F of T minus C square root of LC. Walk on down below. You got the same thing, except there's this extra Z0 that's shoved in there. All right. Z0 works out to be, if you go through the math, the square root of L over C. All right, it's the square root of the inductance divided by the capacitance. Inductance per unit length divided by the capacitance per unit length. So this is very important. What this tells us is that the voltage as a function of location and time divided by the current as a function of location and time is equal to this value Z0. All right. So there is a defined relationship between the voltage and the current. And we know what happens when we take ratios of voltage to current, right? We get resistances, right? Remember, R equals V over I. So this is the ratio of a voltage to a current. So Z0 is going to have units of ohms. This is going to be a very, very critically important parameter for a transmission line, which is why I will box it and say this is definitely something you'll want to memorize. But this has units of ohms. Now, is this a resistance? Is this burning power? No, it's not, right? This is not a resistor that is burning power. It is, however, an impedance. So we're going to define this as the intrinsic impedance of the transmission line. And the intrinsic impedance will tell us that there is a fixed ratio of voltage to current that has to exist for any moving wave along the transmission line. And that's defined by the parameters L and C. Now, let's look at this qualitatively because it kind of makes sense that L and C work the way they do. Right? Think about if the inductance were really, really big and the capacitance were really small. Right? Remember, the inductor is what's going to convert voltage into current, and the capacitor converts current back into voltage. So if the inductor is really big, that means that you put a giant voltage, but you only get a really small amount of current. All right? A giant current and a giant voltage and a small current, well, that's like a high resistance, right? So it makes sense that a high inductance is going to give us a higher impedance. It's the opposite for a capacitor. If we have a really big capacitor, that means it takes a huge amount of current just to get a little bit of voltage. And so that's equivalent to a very low resistance, or in this case, a low impedance. So this kind of makes sense as far as a transmission line. So when we talk about waves on a transmission line, number one, we know what the propagation velocity is if we know what the transmission line parameters are. Number two, we know that the voltage and the current both must exist, and they have to exist with this defined ratio Z0 that we, again, just pops out of the math, but turns out to be very critically important. All right, you can look for a little more details on this in the notes, but it basically just describes what I just said. So with that, we're going to conclude Module 2, and in the next part of this lecture, we're going to talk about different types of transmission lines and how they work.